All right, we're back for another episode today. And today I'm joined by Professor V. Dung, who is at UC, University of California, Irvine. Really excited to have her join us today. It's kind of funny. I was going through like your research interest, just to kind of refreshing myself. I don't even you just do so much stuff. I don't even there's no one thing that you do there. So I will say you probably are most well known for your rhodium and cobalt hydride species to do catalytic reactions. But I mean, there's so much stuff that you guys do at your lab. So it's super exciting to have you on. I guess we'll hop right into it then. Cause you moved, you moved from, University of Toronto. You were there for a few years and then you moved to, UC Irvine. How did you originally get interested in those research interests for the rhodium and cobalt hydride species? How did that kind of idea come about?
Yeah, hey Aiden, thanks so much for having me on your podcast. Excited to be here today and have a chance to chat with you.
Yeah.
So your question about why we started working with rhodium and transition metals when I started in Toronto.
Mm-hmm.
Yeah, so I worked with Dave McMillan as a graduate student, and I really like organic chemistry. And I think at the time, way back then, using transition metals was a little bit more exotic. And so there were people like John Hartwig, Christina White, Melanie Sanford kind of showing how cool, the amazing things that you could do, right? You can activate bonds and make and break bonds that you don't normally think about doing when you think about just traditional organic chemistry. So, on an OChem exam, if a student broke an aldehyde CH bond and did some chemistry with it, they'd probably get marked off. So
right.
that really fascinated me. Yeah. And so then I decided after working with Dave to do a postdoc in organometallic chemistry to learn more about the whole idea of activating bonds with transition metals. And so when we started in Toronto, we kind of continued on that theme. Our original goal was a little bit different. We were trying to actually make Fischer carbenes from aldehydes.
Yep.
And that idea didn't work out. And so we kind of accidentally discovered that you could instead just make these 7-membered rings. And so, yeah, I think to answer your question, it's sort of a mix. And I think this is true for a lot of the different projects in our group. We might have an initial idea or interest, but then the students, just through an iterative process, will discover something or come across something, and then we sort of refine it as we go.
Yeah. I guess what's kind of unique about it is these, I guess, hydride species and activated aldehydes. It doesn't really sound intuitive, I guess, in some respects. You have to. I'm not exactly familiar with how the mechanism works, so maybe we can talk about that a little bit. So I assume you got to have some sort of open coordination site on whatever the metal is. For this case, we can just keep it with rhodium. I guess you bind the aldehyde and then you just activate that carbon hydrogen bond. Is it just that easy? I don't know.
Yes. Yeah. That's a really great question. And that actually does go back to why I was initially interested in this area after working with Bob Bergman and also just all the growing exciting things happening in the area of CH bond activation, functionalization, oxidation. And aldehyde CH bond, it turns out, is not so challenging to activate. So in some of the very original studies by Suggs and others, they were using coordinating groups like pyridines or phenols also to bind the transition metal and direct the activation of the aldehyde CH bond. But depending on the rhodium complex you use, that process is relatively facile and reversible. So you basically coordinate to your transition metal probably through the lone pair of the carbonyl. So that kind of lowers the entropic barrier, and then the oxidative addition can occur.
Yes. Okay. Yes, I was taking a look at kind of more recent projects too you guys are working on. I mean, really cool stuff. I mean, I know you guys, I mean, it's mostly an antioselective kind of catalysis. I would say antioselective asymmetric catalysis. But your work in 1,3-dienes, nickel catalysis. You're doing a lot of copper catalysis. to do was addition of like phosphines like cyclopropane. So I mean, I don't know. I mean, like, is there any like there really you kind of span a lot of organic reactions, or is there anywhere in particular that we can kind of dive into a little bit, or that is going on in your lab right now?
Yeah,
we can dissect a little bit.
Yeah, it's a good question. In some ways, you're kind of touching upon maybe how projects come about and what we're interested in. So because I approach organometallic chemistry more from the perspective of, I think, a synthetic organic chemist, I look at the transition metals as just like they're all fair game in some ways. We did a lot of rhodium chemistry in the past, and part of that was because the rhodium works really well. I think it's a sweet spot, octahedral complex. A lot of phosphine ligands, bidentate phosphine ligands have been developed for rhodium. But more recently, my research team has been looking at some different transition metals. And so it turns out my last name literally means dong in Vietnamese. Sorry, literally means copper in Vietnamese. I was
going to say.
So we've been working on copper chemistry.
Wait, dong means like copper? Wow.
Yeah, it means copper. So I was looking into this during the pandemic, and I came in and I told my students, hey, we're literally the copper group. So I think we should do more copper chemistry. We've done some in the past, but most recently, Ming Hao, Sophia, Julie, Brian, and Sintong have been looking at using copper as a way to activate nucleophiles. So we make very nucleophilic copper phosphido or copper perazolate intermediates through catalytic amounts of base and copper. And then these species can add into like strained olefins. So it's I think it's an interesting way to do asymmetric hydroamination and hydrophosphonation. Yeah. That's a bit different from mechanisms that we previously looked at, where you're really making a metal hydride and then inserting first.
Yeah, I was gonna. You definitely put it well before. It's like there's really no metal you guys honestly don't even touch. So it's like it's hard to like say like, oh yeah, you really do well in this one area. It's like pretty much all metals you've worked with. So I think that's super interesting. And how you do this really for various class of reactions is super unique. I mean you touched on very broad reactions, so it's super cool. How about like an antioselective hydroxylations using like nickel? How did that kind of reaction come about, or how did that kind of pique your interest?
Yeah, definitely. So I guess the way I think about it came from a relatively simple idea at first. Dienes are really useful building blocks for making all kinds of different plastics and polymers, different kinds of materials. Mike Roche's lab at UT Austin has shown that you can take dienes and use metal hydrides to make nucleophilic pi-allyl intermediates. And they've demonstrated really great, total syntheses of polyketide natural products, where this method can take the place of an aldol or an organometallic reaction that normally would be stoichiometric in metal. So our thought was, what if we use the same kinds of building blocks, these dienes, but use metal hydrides that would allow us to access different kinds of electrophilic pi-allyl intermediates. So then this would be a way to add different kinds of nucleophiles, make carbon-carbon, carbon-nitrogen, carbon-sulfur, carbon-phosphorus, carbon-selenium, carbon-oxygen. So it's a wide range of possibilities. And, a lot of groups have, I think, thought about this as well. John Hartwig has some really nice early studies on addition of amines to cyclohexadienes and things like that. And so Xiaowei Yang was a postdoc in my lab who initiated this project in our group. But yeah, she sort of quickly found that with rhodium hydrides, we could make these electrophilic pi-allyl intermediates, and then a whole range of nucleophiles will couple. And so we've gone on to just explore different kinds of nucleophiles. Sometimes we've been surprised. For example, in a palladium catalyzed addition of pyrazoles to dienes, it occurs through a different kind of mechanism. This ligand to hydrogen transfer type mechanism. It was what Alex and Hannah found. And then just along those lines, looking at nickel, we found that nickel could add alcohols to the dienes, and you can generate allylic ethers. What was kind of unique about this study was that allylic ether activation, you make an allylic ether, that is a reversible process. So the nickel can come in and reactivate the CO bond. And so we were seeing really sort of moderate levels of enantioselectivity for a long time. And then Xiaowei discovered that basically by removing the solvent, we could get these transformations to occur under even milder conditions and happen faster. And so we could overcome the reversibility and isolate high enantio, kinetic products, highly enantioselective product ratios. So that it's a long answer to your question, but it kind of starts off with this just basic idea of dienes as interesting building blocks for making chiral allo products. But then you can imagine different mechanisms, different transition metals, and different coupling partners for the diene.
Yeah, no, that's definitely really interesting though, because I suppose once you make the carbon oxygen bond, and then I guess I don't know. I guess it is pretty unique then that the nickel can activate it again. So how does that work then? So you make a carbon oxygen bond, it's reversible, so you're able to activate that again, and then how does the enantioselectivity come in? I know you have a chiral ligand, but I don't know, how does that kind of work? Do you think? Yeah,
for sure. If you have reversibility in your enantioselective transformations, it's not a good thing because over time you're just going to get racemic materials. So you have to get to conditions where that reversibility is really inhibited. So lowering temperature, using the diene basically as the solvent. Those kind of things, I think, allowed us to get into a manifold where it was based on kinetic control. So it wasn't reversible anymore. Yeah.
Okay. That's really cool.
Yeah. I love the idea of reversible reactions going to enantiopure products. And if you're interested in that, Scott Miller, Rob Knowles, and Jiwei Ge in China recently had some really amazing papers. You take racemic materials and you shine light on them, and then you get to enantiopure products. So but in general, that doesn't work without the light. You can't.
You're right. Yeah, this is definitely a unique way of doing my podcast. I usually start with background, but I wanted to definitely touch on your research now because I knew you're a little short on time, so I definitely wanted to touch on that briefly. But perhaps now we can maybe backstep a little bit. Maybe you should actually introduce you because I got excited about your work, but
anyway.
But anyway, so Professor Deng, so you're originally born in Texas, Brigham Spring, Texas, but kind of middle of nowhere. Eventually you did move to Anaheim though. It's kind of really where you really grew up.
Yes.
Thinking about, all through through elementary, middle, high school, were you kind of always interested in the STEM? Any unique hobbies growing up during that time?
So I guess growing up in Anaheim, California, my most unique hobby was I watched a lot of television. That's pretty much all. I had 2 younger brothers and sisters. My parents worked a lot. So I was the oldest, and we pretty much, we would come home and just watch TV from after school all the way till bedtime. And we would do our homework during commercial breaks. So I think that's
I appreciate the honesty.
I sometimes think about that. It's a very, that was my childhood pretty much. It was a lot of sitcoms. Yes. That
Matthew Perry just died. Very sad. I don't know if you ever watched Friends. Matthew Perry just died.
It's really sad to hear.
I
was much older, so when I was a kid, it was Gilligan's Island. I don't know,
Classic.
Three's Company. I don't know if you've heard of those.
I have not, but
I would say, it's kind of sad. I feel like I'm reliving my childhood now because so my son, we actually don't let him watch much TV at all.
Really?
So he has he does gymnastics and he does piano, and he has like, yeah, kind of, yeah. So it's fun to see him doing like, I think maybe hobbies that are more useful than what I had as a hobby.
Right. Well, I appreciate your honesty here, because a lot of like people I talk to, like they'll give me that they like won't say what their actual hobbies were. Like they'll give me something that they like tried or something, or whatever. But like the fact you're saying, yeah, my hobbies were I used to watch a lot of TV. Like I just appreciate that, because like yeah, it's like what else? Like
It's
I'm sure.
really, yeah, it's interesting. I look back on my childhood and that was pretty much sums it up. I mean, I didn't know how to swim, I really had no hobbies. And the funny thing is now I never watch any TV. I think I got it all out like during those high school years. And so now I don't watch any television at all.
Yeah.
So
There you go. But heading into your undergraduate, oh shoot, where'd you do it again? Was it Berkeley? No,
it
hang
was
on.
actually at UC Irvine. Yeah.
Irvine, okay,
Just
okay,
here
that's
in-
where your undergraduate was.
Yeah.
But I think he went in, I'm pretty sure he went in, it wasn't chemistry though. I think he went in like some environmental science or something like that, right?
I did. I started off as an applied ecology major.
Okay.
So it was one of these majors where it was in between the School of Bioscience and then social ecology, because I didn't really know if I wanted to go into the sciences or maybe more of the humanities. And so it was like an in-between major.
Yeah.
But then
okay. Makes sense.
I took organic chemistry with Larry Overman, and he was an amazing teacher.
Legend.
He drew everything up on the blackboard. And just knew the material so well that I realized after taking that class, like I had to keep going in chemistry.
Right. Yeah. So, I mean, when you have Professor Overman as your organic ice, like, that impression it must have left on you must have been crazy.
Yes.
Did you do any like undergraduate research with him, or like how did that?
Yes. So after
Okay.
I took his class, I had a really fantastic a TA named Adam Tomasi, and Adam. Actually, yeah, I was in his lab class. It was a Saturday, I think 8 or 9 hour class. And then
What
Adam said, yeah, it was kind of intense back then. So yeah, Adam said, hey, why don't you get
Full-time
involved
job.
get involved in some undergraduate research. And I had no idea. I had no idea that you could get a PhD and get paid to do it. And so Adam,
Right.
yeah, he definitely encouraged me. And then I went to join Larry's lab, and I worked for a student named Andrew McDonald. And then, just learned a lot about, I think just, to me, undergraduate research is kind of designed for you to be really impressed by the knowledge and the skill set of the people around you, like your professors and your mentors, and to realize how little you actually know, even though you think you knew so much from the classes that you took. And so I think that sort of gap that I realized, it was like a very humbling experience, because I thought I was, as an undergrad, I was like, yeah, I know this stuff. I'm really good at OChem. So that realization that there's so much more to know, I think that was the most important part for me.
I completely hear that point. When I first, because Brad Kerr is my advisor, and I was telling him like, man, like coming out of undergrad, I got, I've like a Bachelor of Science in Chemistry and Chemical Engineering, yada, yada, yada. That doesn't mean crap now. Like it doesn't mean anything now. It's like, you think you know everything. you think you know everything coming out of, like your bachelor's degree. And no, you're like, you don't know anything yet. So it's very,
Right,
it is
right.
true. Very, very humbling experience. But it's also like that hunger or like that thirst for more knowledge too is real as well.
Yes.
And so I definitely hear
I was
that.
always struck by, completely. I remember talking to Bob Grubbs once, and he said something like, there's so much more that I'm learning about olefin metathesis, right? And I think that's just like an amazing attitude, right, to have, right? Here's this Nobel laureate who pretty much defined the field, and he's saying like there's so much more to learn. So I think that's one of the funnest parts about being in the sciences.
Right. Especially like, I mean, I can't really speak on the other STEM fields, but certainly chemistry, it just never ends, honestly. And like that can either be really scary or really, really like really scary or like really hopeful, I guess, because it's just like it never goes. And and so it's always excited to see like what will come next. So, but yeah, so you're
Mhm.
a young, impressionable undergraduate seeing Overman's lab. I mean, that must have been, it must have been really impressive, I guess. Like, I mean, because I know they do a lot of, well, like natural product synthesis for sure, and reaction developments. So, I guess, how did it feel like doing the undergraduate labs and then seeing like, let's say, a real like academic lab? Like, what was that kind of like? What was that kind of feeling?
Oh, yeah. I mean, I actually really did not enjoy the undergraduate laboratory component of my courses.
Mm,
Um, I think part of it was just repeating things and doing stuff on small scale, and I just always was not so excited to be in the lab. But once we entered the research lab, it's just, yeah, it was a completely different environment where you're doing things for a reason, and exploring things that you don't know whether or not they'll work. So that was all
right.
super exciting. I remember talking to one of my mentors, Sylvie Lee, who's now at Pfizer, but she was asking me why I was so excited about taking an IR spectra. And I remember saying, like, this is so exciting because I'm the first person in the universe to characterize this compound by infrared spectroscopy. This
Oh
has never
wow.
been made before. And she was like, all right, that's cool. you know, so I think it was, yeah, that sort of like, I'm doing stuff that no one's done before. That was really
Right.
fun.
Yeah, that's got to be super exciting feeling. And hopefully, I mean, you definitely never want to lose that feeling too. I mean, that feeling of like, oh, no one's done this is certainly like, I mean, in some ways, it's kind of like a drug. Like you definitely want to keep doing that. Absolutely. But that's super cool. Now, kind of being in those doing undergraduate research, was it kind of a natural progression then to do like graduate school with a professor? It was Professor McMillan, right? I think he was at Berkeley at the time, but was that kind of like a natural progression
Yes.
then?
Yeah.
Okay. Yeah.
Yeah. I think maybe like a lot of students, I did um, struggle with the idea a little bit. Like I thought maybe it would be good to get a job afterwards and get some industry experience because I hadn't really had a chance to work in the chemical industry to see what it was like. And so I did think about that. But in the end, I ended up applying to grad school and then going to Berkeley and working for Dave McMillan. So
hmm
yeah, it turned out well.
Was it how did you, I mean, I assume maybe you wanted to stay like on the West Coast, I mean, in California, but coming to Berkeley, I mean, was that, what were kind of some of the decisions like leading into that? Like why Berkeley and then why also McMillan's lab?
Yeah, so I visited Berkeley and I really enjoyed the atmosphere. There was just a lot of just fantastic students. They all seemed really excited about what they're doing. And I think being from California also, even though it was the Bay Area, which is pretty different from Southern California, it still had a bit of that California um, culture to it. And
Yeah.
so it was a very exciting time to be at Berkeley. Carolyn Bertozzi's group was also like a new lab at the time. Dave
Mm.
McMillan, Jeff Long's group was starting up. So yeah, I remember, yeah, meeting John Ellman, and
Oh wow.
yes, it was just like Berkeley's still a fantastic place, but yeah, back then there was just like so many cool people that I met and exciting
It's like lightning
science
in a bottle.
happening. So what was that?
It's like it's just like lightning in a bottle. Like it was just like, it seemed like just so many people there at one time, like it's caught lightning in a bottle.
Yes,
That's really
yeah,
cool though.
yeah, yeah.
Um, Now, during your time there at Berkeley, I know you're doing some, what is it, like Zwitter ionic, I think some rearrangements, some total synthesis. Um, I'm not as familiar with like, I
Yes,
mean, I'm more familiar with Professor McMillan's like photo redox and organocatalysis nowadays, but I don't know. I suppose he
yes,
doesn't
yeah.
really strike me as like a. He doesn't really strike me as like a natural product synthesis guy. So is this? I don't know if this is like a. I don't know. Was this normal? I guess
Oh yeah,
kind of these
um,
kind of reactions.
for sure. Dave has a strong background in natural product total synthesis.
Okay.
He completed some pretty complex molecules with Larry, and if you actually take a look at the McMillan group, sort of like the entire portfolio, there's some really amazing total syntheses that have
Hmm.
been accomplished. And so,
Interesting.
yeah,
Okay.
when I started with Dave, I was also working on some Lewis acid catalysis, Claisen rearrangements. Um, I think I didn't get the memo. I should have probably switched over to the organocatalysis subgroup as fast as I could. But yeah, it was great working with like Kateri, Chris Bortz, Nick Harris. Those guys were all starting up the asymmetric organocatalysis, and it was super fun chatting chemistry with them. And I take credit for having ordered all the solvents that they used in those like, Nobel Prize winning experiments.
They're
Um,
important. That's
but
important.
there was
Yeah.
a yeah, there was actually there was a group of us. So Teshik Yoon, Tristan Lambert, and we were all working on the Lewis acid catalyzed Claisen rearrangements and those different kind of variations. And I think, looking back, as a grad student, you get really excited about your project and, kind of like determined, right, to
Yeah.
complete it. And
Hmm.
it's, yeah, but I definitely was, like always pretty jealous about the things happening in the organocatalysis subgroup.
Sure. I mean, especially like where it's like gone. I definitely like understand that sentiment for sure. Um, but I think, I mean, and like I don't think anyone really could have seen how it really blew up. I don't know. I mean, maybe there were like whispers of it, but like I don't know. I don't think anyone. I don't know. I find. I mean, maybe you can comment on this. I find it hard to believe like where it's like, oh, this project's gonna like just blow up and change the world. You know what I mean? It's gonna like completely like change the way we look at chemistry. I don't know. Maybe there was at the time, but
I will say at the time, Dave being an assistant professor, super, new to the job too, is very impressive looking back. Dave really, really believed in the idea. And I
hmm
remember him coming in and saying, like, this will be so cool, like using organic molecules for asymmetric catalysis. You won't need to have the same kind of precautions of using a glove box and things like that. So, yeah, I think Macmillan believed in it, and the team did believe. Like,
hmm
there was definitely a feeling like we're doing something important.
yeah, absolutely. I also, I mean, and I don't know. Maybe you can definitely comment on this too, but I feel like the skills that you learn as a graduate student is also like the most important. Like, yeah, like you have your projects, and look, some projects aren't going to obviously aren't going to change the world, but like it's the skills that you learn like as a chemist, like all those techniques, and really being like a part of a team, and that really kind of goes the furthest, honestly. Like, and thinking about chemistry and developing like questions, and just understanding the fundamentals is kind of what's
Yeah.
really important, I think. And look,
Yeah, I think that's a really, really good point. I think that's one of the three things that's really important, right? That sense of that you are constantly learning, you're mastering new skills, you're kind of leveling up, which with each experiment and with each experience you have. And then at the same time, I do think that working on something that's very, very meaningful to you, that you
mm,
think can make a difference and make an impact is also really important. Like that's an
absolutely,
important part of the equation as well. And um, when you
yeah.
when you have a combination of those two things, right, it's very motivating.
All right, yeah, absolutely. Yeah, I completely agree. And those fundamentals of chemistry, if you're excited about those fundamentals, I think you really can transcend, um, you know, your graduate school experience. Um, Now, coming towards the end of like your grad school, was it? I mean, was a postdoc kind of a natural decision for you then? Like, were you kind of thinking about being a professor at the time? Like, how did that kind of all take place?
Yes, yes. I've wanted to be a professor for a very long time.
Mm,
So my motivation wasn't that noble initially, I would say. I was a first generation college student, and my cousin had gone to community college, and then she came home one day and she told me, "You really need to think about being a professor."
mm,
She said, professors, I think they teach like 3 hours a week tops, and they have these teaching assistants that do everything for them. It's a really sweet job. And so I thought, all right, that does sound really good. Like, think about all the TV I could potentially watch, right? So basically,
Jeez.
I had that in mind, that was a sweet job. Yeah. And I remember also even seeing Larry Overman, his office, kind of overlooking Aldrich Park up on the fifth floor of the building. And yeah, seeing him come in, teach like, 50 minutes 3 times a week. And then I thought, this guy has a sweet life. Like, I wouldn't mind having this job. This looks really good. So I've always kind of wanted to be a professor. Just I do enjoy the teaching aspect of it, the freedom. And then also after grad school, I would say Dave McMillan definitely made it look really, really fun.
Yeah.
And so the postdoc was the next kind of natural step. And I wanted to do something a little bit different in terms of, instead of working for a brand new professor, or work for someone who was really established, so I could sort of learn a different way of, just get a different sense of a group culture. And so the Bergman group was my top choice. Bob, kind of funny story. I actually tried to get into Bob's lab as a grad student at Berkeley. He was like, I tried to get into his lab for a summer rotation, but it was too full. So I decided to try again for a postdoc. And I was really lucky that he was willing to take me on. And so that was also just an incredible learning experience. I met so many great people. And then, I got to learn organometallic chemistry. Bob also has a very very diverse research interests, tons of different collaborations. And so in Bob's lab, I didn't really publish any work on CH bond activation, but I worked on a project with Ken Raymond on supramolecular chemistry. So kind of ironically, even though the McMillan group was known for making iminium ions, I ended up encapsulating iminium ions in these supramolecular clusters in Bob's group. And then for my independent career, that's when I started looking at transition metals. So I think I'm just like one of these people that's a little bit behind the trend. It takes me a while to adopt something. So, so we actually didn't start doing any CH bond activation until my independent career. But I was working on something very, very different in the Bergman group. And if Bob ever wins, a Nobel Prize for CH bond oxidation, which I think he's very deserving, I can say that I worked on the iminium ion chemistry.
Well, your lab's leading a lot of stuff now. So it took it is kind of funny looking back now. It's like you becoming a professor. Maybe when you were younger, you didn't have the most noble goals, but you sure as hell had to work hard to get to where you're at now, though. So it's not while you do have a luxurious lifestyle, it's not easy to get to by any stretch of the imagination.
For sure, Aiden. I think I learned afterwards that actually it's not just the teaching a few hours a week that we do. But I really do love the job. And if there are any students out there kind of thinking, maybe I'd like to be a professor, I think it's a really great job. And a lot of us might talk ourselves out of it because there's all these like, oh, maybe I can't do it. What about funding? What about, how do I come up with ideas? And I think it's one of these things where, if you're interested in it at all, just kind of don't talk yourself out of it and give it a chance.
Yeah.
Because I think most professors we all had the same sort of thoughts. Like, oh, it's going to be hard to, think of ideas. It's going to be hard to like mentor students. And it's all very, very challenging stuff, but it's all very, very meaningful at the same time. And I think that's one of the things I like about the job is like, there's always that opportunity, right, to like kind of find ways to do it better.
Yeah, absolutely. I just want to make sure do you have to go? Does you have the next appointment or?
I'm actually going to be popping up to see one of my first graduate students, Charles Young. He's a chemist at Merck.
That's awesome.
He was my first grad student. And it's pretty amazing. We have a collaboration with him right now. And so I'm going to pop over and chat with him about some bioisosteres. But it was really fun chatting with you, Aiden. I do appreciate, what you said about trying to kind of bring chemistry out to the general public a little bit. And one thing I've been thinking a lot about, like I teach this class that mostly are biology majors, but one of the things I think for me is, the difference between biology, chemistry, and physics. You kind of mentioned like biology is so popular, physics is kind of popular when you think about Earth's planets and things like that, right?
Right. Yep.
I think astronomy is like a very popular topic. But the way you can think about it too is, it's almost like looking at life where you could have a really zoomed out view, right?
Mm-hmm.
You can see like the Earth and the planets, and that's exciting. And then you kind of go to the biological scale, and you've got biomolecules or organisms and animals, but chemistry is like just, it's still the same stuff that we all care about. It's just higher resolution, right? So instead of a protein looking at like a Pac-Man frog, you zoom in a billion times, right? So then you're on the order of atoms and bonds. And I think everyone wants 4K resolution or 5G phones. So why not the opportunity to look at our world with a little bit higher resolution?
That's great advice and great points. I try to bring chemistry more, because I mean, at the end of the day, like people that talk about like medicine or understanding these organisms, at the end of the day, they're just carbon, hydrogen, oxygen, and atoms, and like that's kind of what we do. And then for like physics and astronomy, like that's like huge ground level, but again, their composition is just carbon, hydrogen, nitrogen, oxygen, all yada yada yada, metals. So we really just are at the microscopic level, and there's just so much fascinating transformations, you know. Yeah. But Professor Dong, I want to thank you so much for taking some time.
I mean, it was a pleasure. And for any parents out there who worry about their children's screen time, you know, maybe don't stress too much, because I watched a ton of TV and it was okay.
It turned out all right.
Take care, Aiden.
Take care, Professor Dong.
Your research, the literature.
Right. Appreciate it. Bye. Have a good one.